Okay, so let's first talk about representing graphs. Okay, think about this, think about in your computer. Okay, so in a computer. Okay, so the first obvious way is to just, list. So you have a list of vertices, V, and a list of edges where each edge is a pair, and a list of edges where each edge, where each edge is a pair. Okay. Now there are some other convenient ways in which we can sort of represent graphs. Okay, and one of them is called the adjacency list. And the other is called the adjacency matrix. Okay, and they're basically both different ways of telling us what are the relationships. So let's work with our friend, our old graph. Okay, V1, V2, V3, V4, V5, V6, V7. Okay. And what the adjacency list does is it says, like, I'm going to give you a list of my vertices. So I'm going to give you a list of the vertices V1, V2, V3, V4, V5, V6, V7. So that way I've told you what are the vertices, what are the objects, what are the people. Okay. And now for each vertex, I'm going to tell you who are they linked to. The people that, or the objects that a vertex is linked to is typically called their neighbors. So I'm going to tell you what's the neighborhood of vertex V1. So V1 is connected to V2 and V5. So V2, V5. V2, V5. V2 is connected to V1, V3, V4, V1, V3, V4, V5. V1, V3, V4, V5. Okay. And then, so let me write this slightly more legibly, V7. Okay. And then V3 is connected to V2, V4. V2, V4. And then V4 is connected to, as neighbors, V3, V2, V5. So V2, V3, V5. Okay. And V5 is connected to V1, V2, V4. V1, V2, V4. And finally, V6 is connected to V7, and V7 is connected to V8. V7 is connected to V6. Okay, so for each vertex, I tell you who they're related to. You'll observe something interesting. Let's say we count up the number of objects that appear as neighbors. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's exactly twice the number of links. 1, 2, 3, 4, 5, 6, 7, 8. 8 links. 16 total neighbors. Okay, and you can think, why is that? Why is that? Well, let's see. So for example, V6 is a neighbor of V7, so that's the link V6, V7. But that link is represented a second time when we consider V7, who is linked to V6. So you see that every link, so for example, let's consider the link V1, V5, that appears as V5, V1. So every link is represented twice in the adjacency matrix. Okay, well, that looks a little bit redundant, It looks a little bit more redundant than simply a list of vertices and a list of edges, which represents each vertex once and each edge once. Okay, so there seems to be a little redundancy, and that's a price we pay in order to have quick access to a particular vertex. Because, for example, if I ask you, what's going on with vertex 7? So you just, what's going on with vertex 5? You go to vertex 5 and you say, oh, this guy is neighbors of, is neighbors with 1, 2, and 4. You have instant access to the neighbors if you store this in, say, a vector or an array, and then you can store this as lists. So as lists, corresponding to each vertex. So you could store this as a vector of lists. Okay, and you have virtually instant access to a vertex and the vertex's neighbors. Well, on the other hand, if you just had a list of vertices and a list of edges, and I asked you, okay, what's going on with vertex 5? You'd have to search through the whole edge list to figure out who are neighbors with vertex 5. Okay. So that we pay a little bit of a price in terms of redundancy, but it gives us quick access to the vertices. Let me show you about the adjacency matrix. The adjacency matrix is very similar. Okay, it's just a matrix. Okay, and it assumes that the vertices are labeled V1 up to V7, but I'll put the labels here: V1, V2, V3, V4, V5, V6, V7, V1, V2, V3, V4, V5, V6, V7. It's matrix. Okay, and you know, if you go to any entry in this matrix, I'm going to require this entry in the matrix to be either 0 or 1. 0 if there's a link between the two vertices, and 1 if and 0 if there's no link between the two vertices, and a 1 if there is a link. And we can construct this adjacency matrix directly from the adjacency list, because look, V1 is connected to V2 and V5. So typically, the graphs that we're talking about don't have links to themselves. A node doesn't have a vertex does not have a link to itself. That's what's called a self-edge or a loop. So we don't have loops. So there's no edge from V1 to V1, but there's an edge from V1 to V2 and V5. So V2 and V5. The others are zeros. Okay. So V2 has edges to 1, 3, 4, and 5. Okay. So has edges to 1, 3, 4, and 5. Okay. Then V3 to 2 and 4. So V3 has an edge to V2 and to V4. Okay. And then V4 has an edge to V2, V3, and V5. So V2, V3, and V5. Okay. And then V5 to V1, V2, V4. V1, V2, V4, and no other edges. Okay. And V6 has an edge to V7. And V7 has an edge to V6. Okay, and there. You see, for every vertex that appears in an adjacency list, in a list of adjacencies, of neighbors, okay, every vertex that appears here will appear here as a 1. Okay. Now, if you look here, you see, oh, lots of zeros, so lots of redundancy, lots of, in theory, lots of, or in practice, there could be a lot of wasted zeros, lot of redundant zeros. Okay, if we think about memory, okay, in here, the amount of memory being used is n for this list, okay, and in this case, n is 7. And then however many edges there are, twice that number. Because remember, each edge appears twice. So memory here is, roughly speaking, the size of the vertex set plus twice the size of the edge set. The memory here is just n squared. Memory is just n squared. Okay, so in theory, there could be n squared edges, an edge between order of n squared edges, an edge between every pair of vertices. But in practice, most graphs we encounter are what's called sparse, so lots of zeros here. Okay, so we're paying a price in terms of memory. What do we gain here? So here we had instant access to a particular vertex. But if I asked you, okay, so for vertex V4, is vertex V5 a neighbor? So now you instantly access V4. Now you need to trudge along this list. And oh, yes. But if I said, what about V6? You have to trudge along the list and come to the end and say no. So you have to perform a list search in order to decide whether V4 is a neighbor of V5 in this representation. In this representation, because it's an array, you have instant access to the array location 4, 5. You look at it and you see 1, you know. So this gives you quicker access to individual neighbor links, okay, at the price of extra memory. Okay, let's talk about degrees. So degrees. Okay. So the degree I already mentioned is the number of neighbors, or it's the number of links that connect to a vertex. So in this case, we can list the degrees. So all the degrees. So there's a degree. So we'll use the label delta. So we'll say delta of V1 is equal to 2. Okay, delta of V2 is equal to 4. Okay, delta of V3 is equal to 2. Delta of V4 is equal to 3. 1, 2, 3. Delta of V5 is equal to 1, 2, 3, and delta of V6 is equal to 1, delta of V7 is equal to 1. Okay, and we typically say that this sequence of degrees is, can be represented by the degree sequence. And if I go from smallest to largest, I will list the degree sequence as 1, 1, 2, 2, 3, 3, 4. So this is the degree sequence. So we got a lot of notation just telling you about graphs. Okay, so this is the degree sequence. Okay, and basically I list the degrees in increasing order. Okay, and sometimes we can ask questions like, I give you a degree sequence like, okay, 2, 2, 2. So here's a degree sequence, 2, 2, 2. Okay, construct a graph with that degree sequence. So I'm asking you for a graph. Okay, the first question is how many vertices in my graph? You just look at the number of degrees. There's 3. So it's a graph with 3 vertices. So there's 3 vertices. That's instant. Okay, now one vertex of degree 2, one of degree 2, one of degree 2. Okay, so we need to find 3. All 3 of the vertices have to have degree 2, and the only way to do that is here. So this vertex has degree 2, this vertex has degree 2, this vertex has degree 2. Okay. You will note again that if you add up these degrees in the degree sequence, then you get 1, 2, 3, 4, 5, 6, 9, 12. 1, 2, 3, 4, 5, 6 plus 6, 12 plus 4, 16. So the sum of these degrees equals 16. Okay, and that's the same number we got when we added up the vertices in the adjacency list, and for a good reason, because the vertices in that adjacency list are exactly the number of vertices in each adjacency list is exactly the degree. So you add up the degrees, you get the same number. And this is, again, it equals twice the number of edges. Okay. Now, so let's play around with this a little bit. I'll give you an exercise. Okay. Construct a graph with degree sequence. I'm just going to pick the degree sequence 1, 1, 3, 3, 3. So there's one vertex of degree 1, another of degree 1, and then the remaining of degree 3. So the first question you might ask is how many vertices are in this graph? So there are 5 vertices in this graph. Okay. And so now you have to arrange the links so that, one vertex, 2 vertices of degree 1 and 3 vertices of degree 3. So go ahead, try to construct it. Pause the video. I'll give you a couple of seconds. Pause the video for as long as you like, but I'll continue in a couple of seconds. So pause the video. I'll walk up and down. So now you've paused the video. And okay, you're back. And if you pause the video and solve this problem, fantastic. You have achieved a miracle. If you pause the video and couldn't solve this problem, well, that's okay. That puts you, in the same boat as all of us, including me. Okay, so it's a hard problem to solve. In general, if I give you a degree sequence, can you construct a graph with that degree sequence? Okay, and I'll say a little bit more about this problem very shortly. Let's talk about ways to represent the degree sequence. Okay, so, well, so, common graphs. Okay, I'll show you some common graph patterns, some common graph types. These things recur, and you'll find, even if you look at a huge graph, like a huge social network, if you drill deep and zoom in on specific areas, you might find these patterns occurring. Okay, so I might as well show you these patterns. The first and very interesting common pattern is what we call the clique before. A bunch of friends who are all friends with each other. So imagine there are 5 people, okay, and they're all friends with each other. Okay, so they're all friends with each other. Okay, so this we call the clique on 5 nodes. So the K stands for the clique. And this is the number of vertices. So the clique, everyone's friends with everyone. Okay, so this is called a clique. Okay, let's show you a whole bunch of these, what's called bipartite. Remember the students and courses they're taking. So if you have some vertices on the left, typically of one type, and some vertices on the right, typically of another type, then you can show the affiliation type of relationship where who's affiliated to who's affiliated to what group. Okay, and here I'm saying that every left vertex is affiliated to every right group. Okay? So this is called this is called a bipartite clique. Bipartite means there are two parts. Bipartite clique, and we use the notation K of 3, 2. Okay, so 3 means I have 3 type 1 vertices and 2 type 2 vertices. Okay. The line. Okay, that's easy. So you have vertices arranged in a line, and consecutive vertices are linked. So we call this the line on 5 vertices. Okay, then the cycle. Okay, so instead of being on a line, now if you add a link from the last node to the first node, you create a cycle. Okay, so this is the cycle on 5 nodes. And the star. Okay, so the star is you have a central node, and everyone connects to that central node, and nobody else connects to each other. So that central node is some kind of a hub. Okay, so a star looks like this. So there's your central node, and everybody else is connected on the outside. And we call this the star on 6 vertices. So there are 5 peripheral vertices and 1 central vertex. So the star on 6 vertices. Okay, so some types of graphs. Let's look at the degree sequence. The degree sequence here is 4, 4, 4, 4, 4. The degree sequence here is 2, 2, 3, 3. The degree sequence here is 2, 2, 2, 3, 3. The degree sequence here is 1, 1, 2, 2, 2. The degree sequence here is 2, 2, 2, 2, 2. And the degree sequence here is 1, 1, 1, 1, 1, 5. Okay. So what's interesting is that the degree sequences of different graphs, that have different sort of structures are very different. Okay, and that suggests that the degree sequence of a graph is telling you a lot about the graph. It's some kind of a signature. Okay, so let's see a nice convenient way of representing the degree sequence. So one way to represent the degree sequence here for this graph is to say, I'm going to tell you how many vertices have degree 1, how many have degree 2, how many have degree 3, 4, 5, 6, and so on. So I could even have some vertices which have degree 0, loners, total loners. Okay. And we typically plot that on what's called the degree distribution. Okay, so think about it this way. So there's 0, degree 1, degree 2, degree 3, degree 4. Okay, and how many vertices have degree 0? Well, there are none. Okay, how many vertices have degree 1? So I'm going to go 1, 2, 3, 4. So how many vertices have degree 1? 2 have degree 1. So 2 have degree 1. Okay, how many vertices have degree 2? 2 have degree 2. So 2 have degree 2. Okay, how many vertices have degree 3? 3 have degree 3. Okay, and how many vertices have degree 4? 1 has degree 4. Okay, so this sort of bar chart represents the degree distribution. Okay, sometimes we normalize the heights by the total number of vertices. So this number would become, we normalize this by the total sum of the degrees, and so this number would become 1 over 16. 2 over 16, 2 over 16, 2 over 16, and 1. Sometimes we normalize by a percentage. Okay. Let me show you the degree distribution of some real-world graphs. Degree distribution of real-world graphs. Okay, and I'll just show you two, and you can see these, more accurately drawn in the text or on the slides. Okay, so the first one is the road network, and you can pick a city like, let's say, Pennsylvania, or a state like Pennsylvania, or something like that. So road network. Okay, so if I plot the degree of a node, so you might ask, well, what the hell is a road network? Okay, so in a road network, you have points of interest. For example, intersections. Okay. And, when there's a road that connects two intersections, we'll put the link. So the link is exactly a road, and the points of interest are the vertices. So this is what a road network might look like. Okay. Let's say in some state like Pennsylvania or New York. And we would say that, okay, in this road network, this intersection has degree 1, 2, 3, 4, 5. So that means that at this intersection, 5 roads converge. Okay. So this is what the degree of distribution looks like. So you have, points of interest, intersections with, degree 0, you could have degree 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. Okay. And, so some roads, some points of intersection, some points of interest are sort of at dead ends. And so they connect to, let's say, an intersection. So that road, that vertex has degree 1. So there are a few that have degree 1. Okay. But, and degree 2, a degree 2 intersection looks something like this. So it's just a road continuing. So here's an intersection, and, it's a point of interest, it's interesting, and here's another point of interest, another point of interest, a road connects to this, and then a road leaves. So degree 2. So, but there aren't that many of those. Okay. The interesting points of interest, the interesting intersections have degree 3, 4, 5, and so on. And it turns out that degree 3 is the most common type of intersection. An intersection where, 3 roads converge, 3 roads join. It turns out, so boom. Very large number of degree 3 nodes, and then degree 4 nodes are pretty common too. Okay, so what would a degree 4 node look like? A degree 4 node is some kind of a 4-way intersection. Think of a road, think of Manhattan. Okay, so this guy here is a degree 4 intersection. Okay, so that's pretty common, but 3 is the most common. Okay, but then here's what's interesting. You got a few 5s, you got a few 6s, you got a few 7s, and some 8s, and some 9s. What? Yeah, there are 9-way intersections. Imagine a road network, an intersection where 9 roads converge. Okay. But that's about where it ends. Okay, for a good reason, just physical constraints. Okay. So this is sort of a picture that represents, the road network. Let me show you the picture that represents another kind of network, a kind of a social network. So, for example, the collaboration network. Okay. Collaboration network. Okay. And in particular, the collaboration network or the web network, they all have very similar structure. Okay, so you can build a network from web pages, between web pages, if one web page points to another. You can build a network between people if they collaborate. Let's say they're co-authors on a paper. So 2 people, person 1 and person 2. There's a link if they're co-authors on a paper. Okay, so what does the collaboration network look like? Well, it turns out that, there's some typical number of collaborators a person has. Okay, and so, you have people with a small number of collaborations. So there's 0 collaborations, something like 1, something like 1, 2, 3, up to, let's say, about 10. 10 is approximately the most common. Okay, so like that. So the most common number of collaborations a person has, and it's sort of increasing up till there. Okay, and then it starts decreasing. But it starts decreasing very slowly. Oh my God, slowly. And you can go all the way. There are people who have 40, 50, 100, 150 collaborations, 40 plus. Okay. And what you'll see is that this network, the road network, drops very fast. And this network, well, it hits a peak, okay, so there's a peak, but then it's dropping pretty slowly. What that means is that, there's a typical number of collaborations, but there are always these people who collaborate extensively. This is what's called a heavy tail or a power law. Okay? A power law degree distribution. Okay, so just to show you that, degree distributions tell you a lot about, the types of networks you're looking at, and here are the degree distributions of some, real-world networks. You can form networks out of almost any real-world scenario where you have objects and relationships. And you can see the very big difference between these networks. And that suggests that the degree sequence, the degree distribution of a network is a signature. And in fact, we find that that is roughly true in practice, that different networks that function in different ways have different signatures, have different degree distributions. Okay, so let's erase and come back. And I want to tell you about the theorem of the day, which is the fundamental handshaking theorem. Fundamental property of graphs.